This is a quick video on how to use simple linear regression.
And multiple regression.
I'm only going to cover the conception part of it, as opposed to looking at the formula. So to begin with, simple linear regression is when you use correlation data to predict or infer that something is going to happen. These are the steps for simple linear regression. The first step is to predict that something is going to happen. That is the hypothesis, to look at the research question. The second step is to look at the sample data to deduce which is the dependent variable and the independent variable. Both must be numeric and be related or correlated. Number 3, or step 3, is the univariate analysis. That is where one must look at the descriptive and graphical summaries, such as the histogram and box plots, and to check normality, variability, skewedness, kurtosis, and unimodality. Skewedness is whether the normal distribution is leaning from one side or leaning to another side. Kurtosis is how it's about the shape of the normal distribution, whether it's flat or whether it's pointier. And unimodality, as in just one mode, one peak. Okay, the fourth step is the bivariate analysis, where you use the scatter plot to look at monotonic, the linearity of the relationship, the direction, the effect of x on y, the strength, the gap, and the outlier. Then you calculate the correlation, coefficient, and significance. Basically, steps 3 and 4, we want to try and tick off whether the graph, whether it be like normal distribution or scatter plot, whether it fulfills certain assumptions. And in fulfilling these assumptions, then we could proceed to the next step in simple linear regression. So step 5 is to look at the regression model. I said we're not really going to look at formulas. Well, I lied. So in the regression model, we look at y hat, which equals a plus bx plus e. This is to look at the line of best fit. And y hat is just the y variable. A is the y-intercept. B equals the slope or gradient of the independent variable, and E is the error or the confound. As you can see, the y hat equals a plus bx plus e is very similar, or well, it's actually exactly the same as looking at the equation of a straight line on a Cartesian plane, as in the y equals mx plus b. It's the exact same formula, because we're just looking at a straight line. Anyway, as in, the next step is to use ANOVA to test the significance, as to see whether the regression that we have is of statistical importance in a way. So the beta significantly, to see whether the beta significantly differs from 0. We also look at the effect or the usefulness of this regression. This is through looking at R squared, which shows how variation is accounted for by the independent variable. And then for step 6 of the simple linear regression is to check the residual assumptions, to look at normality, homogeneity, which is whether, or it's basically the variance of the residuals, whether there's equal variance of the residuals. And we also want to look at linearity and the independence of residuals. We don't want residuals to be from the same result, as in we don't want the same result twice in a way. So that's what it means by independence of observations or residuals. And then the final step, step 7, is to interpret or conclude, which is as to see where all the assumptions are fulfilled, and then deduce what is it that we found in this regression. Multiple regression is where we look at dependent variables having more than one predictor. And in there we need to consider multicollinearity. We want to look at the unique variance, and we can use a Venn diagram for overlap, as in to see whether the many different independent variables overlap with each other. And we use the same steps as simple linear regression. Our hypothesis in a multiple regression would be that HO has, as in this is the null hypothesis, has mu1 minus mu2 equals 0. Basically stating that there is no difference between the average of variable 1 and the average of variable 2. In that both IVs, both independent variables, would equal 0. There's no difference between them. And also that they don't really have an effect. The thing about multiple regression though is that we need to standardize the betas into z-scores or others for comparison. And we also have to have an extra degree of freedom because, well, the reason why we need to standardize these scores is that different independent variables, their results do not necessarily line up. As in, maybe their observations, the number of observations, their sample size might be different. So, yeah, that's an example of a reason why we need to standardize the scores. We need to make it so that we are able to compare the scores against each other. The next step would be to judge the multicollinearity, which is, to define multicollinearity, it's the principle whereby we account for two or more IVs, in which variance is not explained by another IV. If we look at a Venn diagram, it's basically reaffirming that a certain part of the IV is uniquely explained by the IV alone and not by other IVs. So in a way, we're saying we want to look at which part or which section of that in the Venn diagram is explained independently by this independent variable and not other independent variables. Tolerance is the percentage of variance in independent variables to deduce the uniqueness of independent variables, and it's ranged between 0 and 1. Tolerance is equivalent to 1 minus r squared, which I've defined before, and also VIF equals 1 divided by tolerance. The whole point of VIF is to just make tolerance into a larger number. And what we desire is for tolerance to be greater than 0.1 or VIF to be less than 10. Anyway, for the last step in multiple regression, in concluding the results, we want to state the association, the significance level, even for, for example, even for controlling a certain independent variable, and then we would state that the regression model, as in the y hat equals a plus bx plus e, the regression model that we have, and then we would state that we expect our dependent variable increases when, and then we would place beta units for every increase in the independent variable, and then afterwards we would state the standard error and then the 95% confidence interval. So to sum up, I talked about the steps of simple linear regression, the steps being to firstly look at the hypothesis, propose the hypothesis, deduce your dependent variable and independent variable, look at whether the assumptions of univariate and bivariate analyses are correct, then run the regression model, and then test the significance using ANOVA, look at the effectiveness of the model, as in how useful it is, that being the R squared, check for residual assumptions, then interpret and conclude. And also we looked at multiple regression in how other independent variables could affect what we are looking at. And in order to judge the uniqueness of one independent variable, we want to look at multicollinearity, as we account for multicollinearity, and we judge the tolerance as a result of that. And yeah, that's simple and multiple regression in a nutshell. Thanks for watching.